Hi there, for a change a bit of vintage equipment. I recently rescued this from the scrap heap. It's a post office meter, I guess one of the many versions of the BT12D, but there is no model identification anywhere. As you can see from the unbroken cull sticker, it hasn't been tampered with. There's no date on it, so this might well be from the factory. This is the meter as I received it, and as you can see, at least the battery test function seems to work. I was intrigued by an analog meter that needs power, and then of course there's the fuse-blown dangerous voltage lamp. Who wouldn't want such an indicator? It's pretty basic otherwise. DC volts from 2.5 to 250 volts, AC volts from 10 to 500, 3 ohms ranges, and DC current 50 microamps, 1, 10 and 100 milliamps and 1 amp. To assess the condition of the meter, I quickly ran some tests. 2 volts in the 2.5 volt range, and if you look at the 0 to 25 scale, we are spot on at 20. 10 volts range, and now we need to look at the 0 to 100 scale. The needle is at 20 as it should be. Changing to 10 volts and the analog meter responds instantly as opposed to the rather slow digital meter at the back. 25 volts range, and on the 0 to 25 volt scale the needle is at 10, which is correct for 10 volts. 25 volts now in the 25 volt range and full deflection of the meter. In the 100 volt range, using the 0 to 100 scale, the needle is halfway between 20 and 30. I've tested other voltages and there's nothing wrong with the DC volts. This is the meter measuring 5 milliamps in the 10 milliamps range. On the 0 to 100 scale, the needle is right at 50, which is correct. In the 100 milliamp range, the same 5 milliamps are hardly visible, but it is halfway between 0 and 10. Ramping the current up to 50 milliamps, and we are right at the 50 on the 0 to 100 scale, and continuing to 100 milliamps for full scale. In the 1 amp range, the needle is at 10 on the 0 to 100 scale. Ramping it up again to about 450 milliamps, and you can see it reads correctly. Increasing the current further overloads the digital meter's milliamp range, and I better stop before blowing the fuse. So the DC current works fine as well. AC volts now, starting at 10 volts in the 10 volt range, which is correctly shown as full deflection. In the 25 volt range, the needle is at 10 on the 0 to 25 scale. Increasing to 25 volts and the needle goes full scale. In the 100 volt range, the needle is halfway between 0 and 30 on the 100 scale. Ramping it up to 100 volts and we go full scale. I was wondering if 100 volts would bring up the dangerous voltage light, but no. I connected the meter to my isolation transformer and changed to the 250 volt range, increasing the voltage until full scale of 250 volts. Surely that is a dangerous voltage, but no light. Changing it to the highest 500 volt range and the meter shows half scale as expected. Nothing wrong with the AC volts, but the dangerous light needs some more investigation. Last not least, ohms. On meters like this, you need to connect the probes first to zero the meter, which means full deflection, because the ohm scale works the other way around, with 0 at the right and infinity on the left. Here's the first problem: the 2K range does not respond at all. The same is true for the 0 to 2 meg range, but the 20 meg range works. I can zero the meter. 10K and the needle is about at 1, which is correct. 100K and the meter shows 10, which is correct. 1 meg and the meter shows 100, also correct. Something is wrong with the 2 lower ohms ranges. Time to open the meter. I start by opening the battery compartment. And here's the problem. The 1.5 volt cell has leaked and corroded the negative terminal. The 9 volt battery looks okay. Interestingly, there are 3 fuses in this meter. After removing the battery, the damage to the negative terminal is visible, but luckily the contact itself is still there, just totally covered with that white stuff. Another interesting observation is that 2 of the 3 1A fuses are not connected at all. They are spares. This meter was truly meant for being out in the field, and the last thing you want is to have to go back to the shop because you blew a fuse. Probably a frequent occurrence, hence not 1 but 2 spares. Who knows? Here's the culprit, a Duracell Plus. It has a date of March 2013. That's old, but I have Duracell batteries from 2012 which have not leaked yet. Anyway, using first diluted vinegar to neutralize the alkaline residue, followed by water, followed by isopropanol, hopefully removed the gunk. And with the new 1.5 volt battery in place, the 0 to 2 megohm range works. 1K shows us 10 on the scale, which is correct. Zeroing the 2K range, which now also works. 1K is too hard to read. 100 ohms shows us 100. 10 ohms shows us 10. 1 ohm shows us 1. All working now. The reason why only the 20 megohm range worked before is because it used the 9 volt battery. Time to see how this thing looks inside. Even if it means breaking the calibration sticker. No, it doesn't come apart that easily. I think I need to remove the knobs on the front first. The knobs are removed, and now the moment of truth. It comes apart and wow, honestly I did not expect such a neat inside. Almost modern looking. This looks like a pretty high quality standard in both build and components. A decent real rotary switch with 2 layers, good quality trim pots, all resistors 1% or better. The 9 volt battery connects to these 2 terminals here, labeled B1P and B1N, probably standing for battery 1 positive and negative. The meter itself are these 2 wires. The 2 nuts labeled FS1 and FS2 connect to the 1A fuse in the battery compartment. The 1.5 battery is connecting using the 2 nuts on the other side labeled B2N and B2P. There is the red power LED and a neon indicator for the danger signal, which so far has not made an appearance. And finally we have an 8-pin chip, apart from plenty of diodes, the only semiconductor here. This is the MC1776CP1, a programmable op-amp. In case you wonder what the programmable means, it refers to the quiescent current within the op-amp, which can be set or programmed in a number of ways. In this particular instance, they seem to have used the RSet to negative supply method shown here. At least there's a 680K resistor between pins 4 and 8, which would probably result in around 15 microamps. The chip seems to be obsolete, and places that still sell them want a lot of money, between 5 and 20 pounds for just one chip. As for the rest of the circuit, it's devilishly hard to reverse engineer because traces jump all the time between the layers, and most disappear eventually in that monster switch with all its layers. In the end I gave up and tried to find an online schematic, but no luck. It turns out that these linesman meters were made for a long time by many different companies in many different variants. I recommend Richard's radio site if you want to know more about these meters. I leave a link in the description below. My meter must fit somewhere between the timeline where the original 12D morphed into the SA9083. The last incarnation of the SA9083 is still available to buy, for example from Telcom International, in a nice yellow holster. By the way, I think all the meters, including mine, came with leather holsters originally. As for schematics, I never managed to find one for my variant. You see, the indication on the right of the scale shows 20 kilo-ohm per volt for DC and 1 kilo-ohm per volt for AC. These are quite standard values, which many analog multimeters without any electronics achieve, so I did not think the op-amp was for amplifying the sensitivity. 20 kilo-ohm per volt indicates that a meter with 50 microamp full-scale deflection is used, and the fact that this meter's lowest DC current range is 50 microamps fits right in. I tested it and the 10 volt range has indeed 200 kilo ohm internal resistance or 20 kilo ohm per volt. My other speculation was that the op-amp was used as an active rectifier to get around the non-linearity of rectifier diodes at low voltages, but as you can see, the AC scale shows the typical non-linearity between 0 and 1. Besides, the red power light is off in AC mode, so the op-amp is used in all modes except AC volts. So what is this mysterious op-amp used for? In the end, I decided that it had to be a current amplifier, despite the modest 20k indication, and to verify that, I removed the meter from the PCB to test it directly. The meter is connected to my power supply through the large 10k resistor you see. The blue meter shows the current and the meter in the background the voltage across the instrument. Applying 50 microamps of current, and what a surprise, the meter barely deflects. This is definitely not a 50 microamp meter, as I had assumed. To find out what it is, let's increase the current until we have full-scale deflection. 450 microamps for full-scale deflection, and at that current, the voltage across the meter is about 0.765 volts. With that, we can calculate R equals volts over current, that the internal resistance of the meter is 1700 ohms. This means we have our answer. The op-amp amplifies the current to the meter to convert a rather insensitive mechanical meter into one that meets the usual standards in terms of electrical sensitivity. I assume they did that because that way they can use a much more robust instrument which can handle being treated badly in the field. To show what I mean, here's a cheap Chinese 50 microamp instrument in the same setup. With about 50 microamps, we get full-scale deflection. We can calculate the internal resistance of this instrument in the same way and get around 1766 ohm, a value that is very close to the 1700 ohm we measured earlier. So why is this instrument better, at least electrically? Let's look at the 50 microamp meter first. If we want to use it to measure, for example, 5 volts at full deflection, we need to add a series resistor R. What value of R do we need? This is very easy to calculate. We know that to get full deflection, a current of 50 microamp needs to flow through the instrument and R. That means the sum of R and the internal resistor of the instrument of 1766 ohms must be 100,000 ohms. This means R itself should be just 98,234 ohms. The load resistance that the 5 volt supply sees is of course 100k, and that does not change whether we measure 1 volt or 5 volt with this circuit. If we do the same calculation for the 450 microamp meter, we see that the sum of R and the internal resistance must be much smaller, only 11k, and R itself is just 9.4k. This means the right circuit loads the power supply about 10 times more than the left. And as you know, for voltage measurements, the higher the input resistance, the better, because the measured object is less loaded with the additional current through the meter. To make it easier to compare meters, it was decided a long time ago to use the total load resistance, that is R plus Ri, for 1 volt. As you can see, this is 20 kilo ohms for the 50 microamp meter and just 2.2 kilo ohms for the 450 microamp meter. This value is often referred to as so and so ohms per volt because you can use it to get the input resistance of any other voltage range. For example, our 5 volt range for the meter with 20 kilo ohm per volt has an input resistance of 5 times 20k or 100k, which is exactly what we have calculated earlier. And a 10 volt range will have 10 times 20k or 200k input resistance. This works, as you will see in this setup. I changed the circuit to the one we just calculated, and the meter in the background shows the input voltage applied. Apologies for the blurriness, the camera focused on the rear meter. 1 volt, and the meter is about at the 10 mark. 2 volts, and so on. You can see that we have made a nice voltmeter with 20 kilo ohm per volt sensitivity with just one resistor and no active electronics. Now, while this meter is sensitive, it's also very flimsy, not very accurate or linear, and would probably not survive a week in an environment like the BT12D was built for, let alone 20 or more years. One more mystery to solve, that of the danger lamp. The circuit is actually really simple. You see it here. The neon with a 62K series resistor R35 is simply connected across the fuse terminals FS1 and FS2. Here are the bolts that fit into the holes on the circuit board, and if I turn the enclosure around, you can see that the end in the clamps that hold the 1A fuse. Interestingly, the fuse terminals are shortened by the range switch in the off position. They are not shorted in the battery test position, but any of the DC volt ranges shorts the fuse terminals. And the same is true for any of the AC volt ranges. In fact, it turns out the only time the fuses are not internally shortened is in the battery test position and DC current range. Of course, when the terminals are shortened, then the neon is also shortened and it will never light up. The conclusion is that to get the neon to light, we must select an amp range and blow the fuse. Instead of blowing the fuse, a nice Z-bar branded one, no less, I just pulled one end free of its holder. The meter at the back shows the voltage across the input of the BT12D. At 85 volts DC, no danger fuse blown light yet, but at 92 volts DC, the light comes on. For AC, it would be at a slightly lesser 70 volt RMS value. Is this a useful feature? Maybe not so much in the lab, but considering that the meter has 2 spare fuses, probably it was a good thing to have in the field. By the way, the danger fuse blown light does not work in the battery test position. I guess the meter input terminals are simply not connected in that mode because the meter internals are used to measure the battery, and obviously allowing an external voltage or current through would cause trouble. You may wonder if such a meter is still useful in this day and age, but have a look at this. Here I am measuring an AC sinusoidal voltage of 5 volt RMS with my Brymen 869S and the BT12D. The frequency is 100 Hz, now 1 kHz. Now 10 kHz. Now 100 kHz. You can see the value on the Brymen is now dropping while the BT12D is not bothered at all. Now 1 MHz, the Brymen is down to half the voltage while the BT12D is still at almost 4.5 volts. Now 2 MHz and the Brymen is out, but the BT12D still shows about 4 volts on the AC scale. If we increase further to 4 MHz, and now the BT12D is down to half the voltage. Arguably, some low changing values like this 1 Hz signal is easier to see on an analog meter. This very slow AC signal shows that the BT12D uses a single diode and not a full bridge rectifier. A full bridge always has 2 diodes in the current path with the associated double voltage drop. A single diode reduces that, but at really low frequencies you see that it only shows a value during the positive half wave. Oh, and before I forget, the meter came with this tool. I don't know exactly how it is used, but I would speculate that it's for inserting or removing wires in these telecom wiring boxes you see along the street. The tip is probably for pushing wires into connections, while the unfolding hook may be handy to pull a wire out. In case someone can shed more light on the tool, its usage, or if you have fond or not so fond memories of the BT12D, please leave it in the comments. The BT12D won't be replacing my other meters soon, but for occasional special use, a robust analog multimeter may come in handy. I will try using it occasionally in future videos if I can. And that's it for this video. Don't forget to subscribe if you not have already, and maybe consider becoming a Patreon, link in the description. As Patreon you can get early access to videos, a blog and other exclusive content. Thanks for watching.